Hello and welcome to the final part of lecture 34. Just to kind of remind you what we're going to do is we're just going to prove the statement A implies B, maybe that the isometries have this property that they preserve inner product spaces. And the definition of an isometry, going back here, involves inner products. So in order to prove this statement, we're going to need somehow to link inner products with norms. Okay, and so I left off with the following fact that over the real numbers, we can link an inner product to norms using this identity, and over the complex, we can link the inner product to norms using this identity. Now the book does the real numbers, so I will do the complex numbers. Okay, and so let's go ahead and work out the details here. So I'm interested in the inner product of SU and SUV. Okay, now I use the formula, and the formula tells me that this is the same as the norm of SU plus SV squared minus the norm of SU minus SV squared plus the norm of SU plus ISV squared I. And I don't have quite enough room here, so let me squeeze it in. SU minus I SV squared I. And notice that S is a linear operator, right? So because it's a linear operator, so I'm just going to use the fact that I have a linear operator, this is kind of chapter 3 stuff, that I can just rewrite. Here, I'll write it down here. I can rewrite this as S evaluated at U plus V squared. And so I can go through and replace, kind of bring in the values, like rewrite this in terms of using the linear property. Okay, so writing that all out. Oh, and I forgot to put this all over 4, right? Because that should be all over 4. And this is SU minus IV squared I all over 4. And now, remember, isometry means that the length, the norm of this vector is just the norm of the vector u plus v, right? So this here I can kind of, because S is an isometry, I can remove the s's, right? So I can use the fact that S is an isometry to go to the next step. And so I get minus u, the norm of u minus v, plus the norm of u plus iv squared times I, minus the norm of u minus iv squared I, all over 4. But if you step back and stare at that, that is actually the definition for, or the formula again, for the inner product of u and v. So there we go. The inner product of u and v is the same thing as the inner product of SU and SV. Okay, and going the reverse direction is actually pretty straightforward, because what we want to know is, well, what's the norm of SU, right? So we can compute the norm of SU squared, right? That's just simply SU, right? The inner product of SU with itself. And because part B is true, that's the same thing as the inner product of U with itself. And that's just the same as the norm of U squared, right? So this is true for all U. So that proves that if we have this property on inner products, we get that we have an isometry. Okay. A couple final things that I want to point out before we kind of wrap up today's lecture. If A is an orthogonal matrix, okay, then the theorem implies that the inverse of A is simply the adjoint or the conjugate transpose. So this is the conjugate transpose. So when you have a matrix whose columns are all orthonormal, it's very easy to find the inverse. You just take the conjugate transpose, right? So this is just the consequence of part H. And the other thing that we get for free is that every isometry is a normal operator. And the proof is simply coming from the fact that S composed with the adjoint is the identity, but we also saw that this is the same thing as S composed, or the adjoint composed with S. So the order in which you do these operators are the same thing. So that means that S is normal, right? So if S is an isometry. Okay, so that's kind of all that I wanted to talk about today. There are lots of kind of big ideas in here in today's lecture. We had what a positive operator is. We've learned about isometry, and we saw a whole bunch of characterizations of these operators. So that's it for today's lecture, and I'll see you at lecture 35.